0.67 over here, 0.5 over here, it will create the purple color. So once we have the basis vector, any data can be created from those basis vectors, right? Okay, so in case of a PCA, we explicitly created the basis. Once we have the basis, we can represent the data in terms of the basis vectors. Okay, so here, basis was created explicitly. We came up with the covariance matrix, eigenvalues, eigenvectors, right? So now let me show you how can we implicitly have it discover the basis. Okay, the idea is extremely simple. Okay, and it has a lot of beautiful applications that I'll talk about. Okay, so suppose you create a neural network. Input is, again, let's take the case of the MNIST data, 28 by 28, 784 by 1 is our input. Okay, then what we do is, and suppose our goal was, just like the PCA example I gave you, we wanted to reduce it to how many dimensions in case of our PCA? 200. Let's say we also the same goal over here. So what we'll do is we'll pass it through 200 neurons. So 200 neurons over here in the hidden layer. Okay, so now here's the interesting part. Okay, we will put same number of neurons as the input neurons in the as the input data in the output layer. So input data was 784 by 1. I put 784 neurons over here. Okay, so then we train this network. Okay, so remember when we train, we have to tell it what will be the expected output.
Which is supposed to be the same.
It's supposed to be the same. So see, just like that's the whole idea of basis, that if we have the basis, we can recreate the data. So think of this way, aren't weights essentially multiply this by this to get this output, right? So now basically it's learning the compression from 784 to 200. So this is our compression essentially. And then it's learning, decompress it back to the original. So the output, the expected output, when we train it, is same as input. So my question is it supervised learning or unsupervised?
I mean, you don't need a label. You don't need a label.
We don't need a label.
So it's unsupervised.
So it's unsupervised.
Yeah.
Okay. And the beauty is, you can start collecting data. So after it has learned, so think of it this way. Isn't the output over here 200 numbers?
Yeah.
Okay. After we have trained it on many, many digits, okay, output same as the input. Then what we do is, it will learn these weights, right? These weights will be learned. Okay, also the decompression weights will be learned. But we don't care about the decompression. Now simply remove this. Okay, so after the autoencoder has been created, you will see there will be 200 outputs. And now these weights are fixed. We will not change them. Okay, now if I put a 100 neuron classifier over here and a 10 neuron over here, right? Now again, whatever the weight matrix is over here. So how did it learn how to compress 784 into 200? It learned from the data, okay? So now many people have done a mathematical analysis of this approach. And there's, again, a slightly advanced concept called nonlinear PCA. Okay, if I can locate some picture. Remember the bases in a PCA? So this is, let's say, a plane in one dimension, right? If this is, let's say, a plane in another dimension. Okay, for bases are always orthogonal to each other. Okay, so the inner product of these will be 0, right? Okay, so the PCA that I described to you is referred to as a linear PCA. So the planes or the hyperplanes in high dimensions look like this. Okay, they are like straight and perpendicular to each other. Once we go through the autoencoder, just like I showed you the training mechanism over here, then when it does it, effectively if we try to analyze the mathematical behavior of this compression over here, it sort of does something like this. So it still creates the orthogonal behavior, but the planes themselves are nonlinear. They are not flat surfaces. So in a way, it does far better job than the traditional PCA. And second important part is it's very easy to train because it learns from the data. So now, like I said, once autoencoder is trained, we remove the output layer. Now, these weights are fixed, but during training, as we are doing the classification, we will go to the supervised. If we are feeding a digit 2, then this should be 1, everything else should be 0. We'll backpropagate, we'll adjust these weights. Okay, will backpropagate, will we adjust these weights also? No, because they've already learned the nonlinear PCA. We don't want to disturb that. Okay, so in your next assignment, that hopefully by tomorrow so again, don't worry, I'll write all the code. As long as you go through, understand the concept, try it out, see how does it compare to the standard PCA. And so this is our first example of a real useful deep network. Okay, so if you take a look at now, you can argue there are 2 hidden layers and an output layer, right? Why did we have this hidden layer? So that we can do, if there's a decision boundary, we can do a nonlinear decision boundary. As you guys learned from, when I was showing you, if you pick 5 neurons in the hidden layer versus 1 neuron in the hidden layer. So the decision boundary in the reduced dimensional space is nonlinear. These neurons will help us do a better classification. And what was the purpose of this first hidden layer? Reduce the dimensionality, but we made it learn independent of this first, so that it learns the nonlinear PCA, right? Can we use more than one layer inside our nonlinear PCA?
You'll be complicating it more, so no.
First, let's say, is it possible?
Yes.
Yes. How will we do this? Let me quickly show it to you. And then we'll talk about, is it useful? Okay, so let's say what we wanted to do is, from 784 by 1, we wanted to reduce to, let's say, 300 by 1. Then we further wanted to reduce it to, let's say, 100 by 1. So this is the nonlinear PCA, or this is the autoencoder that we wanted to create. Okay. So how will we train it? Input 784 by 1.
2 bases.
Then how many neurons will I pick in the 300? how many neurons will I pick in the output layer? So forget this part, don't worry, focus on this one. Just try to create 784. So input is 784, one, same digit, same output, right? We will train it over and over again for a lot of data. After it is trained, which weights will we fix? So these weights, the compression weights will be fixed, and this we can remove. You guys agree? Yeah. Okay. So now we remove this. Okay. Now we want to create another layer for the autoencoder. So now what will you do? Put 100 neurons over here.
And then 300.
And what will be the output? Yeah, you got it, 300 neurons over here. So now you'll feed in a digit 2. Okay. My question is, for these 300 neurons, what is the expected output during training?
The one that had 7, 8, 4 times weight.
The compression of the.
Yeah.
The compression output.
Yeah.
So if this was 0.2 as an example,
Yeah.
this will be 0.2. If this was 0.1, this will be 0.1. Right? So we'll train it, and as we back propagate, we'll adjust these weights, we will adjust these weights, correct?
Yeah.
So W adjust. Okay, so suppose we went through a lot of training data, we trained it, then what will we do? Remove the last layer, exactly. So now take a look over here. Aren't these the 100 reduced dimensionality from 784 to 100? Now we can create a classifier. Maybe we can put a 50 neurons over here, 10 neurons over here, and train it so that these weights gets adjusted, these weights get adjusted. What about these?
Fixed.
They stay fixed. Okay. So how many layers are you seeing now total? 4 layers. So now this is, like I said, creating a deeper network. And again, from a classification point of view, we are following the universal approximation theorem. We're not picking more than one hidden layer to do the classification. Okay. The purpose of these is simply to reduce or perform the nonlinear PCA in a better way. Okay. So coming back to the question, is it useful to have more layers in the autoencoder or the nonlinear PCA? And the answer is it depends on the data. For more sophisticated data, very high dimensional data, it will work out better. If it's a simple digit type of data, you won't see a benefit of going to one more hidden layer, right? Okay, so now let me show you just a couple more minutes, then I'll give you a break, is some neat applications of this idea. Okay, one idea, one concept that I showed you over here is because we are reducing the dimensionality, automatically it's trying to learn as it's trying to compress the data. What parts are important, right? So we'll definitely keep all the important information and not worry too much about the background, what color is it. So it learns from the data what is important during training. So that's a good part. More data we have, it will learn a great job, right? So now let me show you some applications of it. Okay. By first asking you a question. Suppose you created autoencoder followed by a classifier, just like I showed you. Okay. Then, or actually, let's remove the classifier for the time being. Okay, from 300, we went to 100. Then we'll go back to 300. And let's say we go back to 784. So we're just looking at the autoencoder. Can we train this network in an unsupervised manner? Again, think of what's the definition of unsupervised.
One label.
No label.
Yes.
Yes, so, yeah.
Yes, why
Why
not? Just give it a 2, and this will be 2, this 3, this will be 3. Sure, we can train it, right? After it has been trained, suppose you feed in a digit 5, which it had never seen before. It had seen other 5 digits during the training data, but not this particular 5. If I go over here and take a look at what output it produces, what's your guess, what will it look like?
It should be fine.
It should be 5 because that's what we trained it on, right? Okay, so we'll still look at fairly decent 5, very similar to this 5. Okay, if I did, for example, a mean square error between this and this, what will be my mean square error? Will it be high? Will it be low?
No.
It will be low because it is reproducing the data, right? Again, the analogy is you compress a file, you decompress a file, and you find out what's the difference between the decompressed and the original. If it's a good compression, it should be the same. So if this is the same as this one, provided we have trained it nicely, it's a good training, mean square error will be very low. Okay, so suppose we trained it all the digits, does a beautiful job, we give it unknown digit, gives us, right? Now, what if somebody gives us a picture of a cat? Whatever the cat looks like, I can't draw the cat, but pretend it's a cat. My question to you is, what will it look like on the output?
I don't think it will be a cat.
No, 0? I think 0.
It will be some image, but will it be like a same cat that we...
No.
If I did a mean square error, what will it be?
High.
Right? So now let me show you a security application of this, okay? So let's say you wanted to create a real-time network monitoring system where, remember, as you send an email, it gets converted to packets and then goes to whatever the destination is. What if some hacker comes in and injects something into the packet? Right? So what if this is now, remember data is just vector, right? So we took a packet over here, a communication packet, which has not been tampered. And we train our network on normal packets, which have never been tampered. What will be the MSC?
Low.
Low. Tomorrow somebody, hacker comes in, injects the data. What will be the MSC compared to the previous case, non-tampered case? High. So this is, many researchers are doing this. In fact, a paper last year used this concept to do traffic monitoring as an example, right? Okay, so security could be, images, could be packets, doesn't matter. So the important thing for you to remember is, once again, let me summarize. We can create the basis vectors of ourselves by following the eigenvalues, eigenvectors. And once we have the basis vectors, any input data can be reduced into a lower dimensional space. So that's perfectly works. Whatever we get out of it is referred to as the linear PCA. Okay. On the other hand, if we created an autoencoder where in the beginning input size is the same as the output layer, and we train it in an unsupervised manner, whatever the input is, expected output is the same. Once we train it, we remove the output layer, and some people have done very detailed mathematical analysis on it, have mathematically proven that this indeed is doing a nonlinear PCA implicitly. Okay? We won't worry about going into the mathematical proof of it. We'll just take their word as yes, it is doing nonlinear PCA, whose job is to do dimensionality reduction, which you can easily intuitively see If we remove the output layer, yeah, from 784, we went to 300 dimensions. From 300, we went to 100 dimensions, right? Obviously, now it has learned to keep the most relevant parts of the data. And now if we attach a classifier to it, we can classify a lot better, as you will confirm in your next assignment. Okay.
So how will you decide the dimensional reduction size based on input data?
It really depends on the type of data. Okay. For example, there's one practical problem. I'm working for a company where the features are such that there's high uncorrelation between it. So I have to use a lot of components over here, because if I try to reduce it too much, I start losing the important information. But if it is a MNIST type of digit type of data, which is a very easy data set, you can easily reduce it to 100 dimensions or 50 dimensions and still have it do a great job.
So basically it works on the trial and error basis.
Trial and error, and also the complexity of the input data, the classes of input data, how similar or how different they are. All right, let me give you guys a break, and then I'll cover one more small thing.